Hi, what are you talking about?
你好，老师。Hello，老师。
你好，Hello，
你好吗？
我很好，你们呢？
我也很好。
哎，谢谢。I mean, yeah, you have made a great progress in your Chinese, I think.
啊，谢谢你。
For the fifth chapter, we talk about the system modeling. And at the introduction, we have said that we develop different models to represent the system from different perspectives. We have talked about four perspectives: an external perspectives corresponding to context models, an interaction perspectives corresponding to interaction models to model the interactions between our system and its environment or between the components of our system. We have also talked about a structural perspective corresponding to structural models, where we model the organization of our system or the structure of the data that is processed by the system. And the last perspective is a behavioral perspective corresponding to behavioral model. With behavioral models, we have the dynamic behavior of the system and how it responds to events. These are four perspectives in this chapter. And also we have talked about some diagrams. Do you remember the 5 diagram types proposed by UML users to represent the essential of a system? Yeah, we have asked the same question the last class. Case diagram, and perhaps you want to say use case diagram, yeah? To see the interactions between our system and its environment. Yeah. Use case diagram is one of the 5 diagrams and class diagram, but object diagram, no, we don't have an object diagram in UML. Activity, yeah, very good, Kaya. Activity diagram to show the activities involved in a process or in data processing. Till now, you have cited 4 diagrams, yeah, and state diagrams. Thank you, Kaya. Yeah, perfect. Activity diagrams, we have talked about it in the context model. Yeah, we talk about the activities involved in the process or in data processing to define the boundaries of our system. Then for use case diagram and sequence diagrams, we have used them in the interaction model. Use case diagrams to show the interactions between our system and its environment. Sequence diagrams to show the interactions between actors and the system and between system components. Later, for the class diagrams, we have also talked about it. In the last class, it's for the structural model to show the object classes in the system and the associations between these classes. The last one is the state diagrams to show how the system reacts to internal and external events. We'll talk about it in this class. And these are the 5 diagrams to represent the essentials of our system. And yeah, it's also important to know the features of each diagram. For example, for the activity diagram, the starting point is indicated by a field circle, and the ending of a process is indicated by a field circle inside another circle. Rectangles with round corners represent activities. And we have arrows to represent the flow of work from one activity to another. Yeah, pay attention to these details. Also for the sequence, use case diagrams to show in use case diagrams we have different actors, and for the sequence diagram we read the class diagrams in Java core labels. That means either we can represent it simply, like what we have shown in the last class. Yeah, okay, I will return it. Here is the sequence diagram in detail. And then for a structural model, we can have a simple class diagram like this, just to show two classes, patient and patient record, with an association between them. We can also have more details. For one class, here is a rather complete system, and then for a single class, we can detail it like this. We can list the attributes and the methods corresponding to the class. And we have the associations between class, like generalization, aggregation. Yeah. And we have said the generalization is like what we have said before, inheritance, and aggregation is for the relationship between the parts perspective. Behavioral models are models of the dynamic behavior of the system as it is executing. They show what happens or what is supposed to happen when a system responds to a stimulus from its environment. Here, it's important to note that firstly, we describe models of the dynamic behavior of a system. Secondly, the activities here or the behaviors here is to show the reply or the response to a stimulus from its environment. So what can be the stimulus? We can think of the stimulus as being of two types. The first one is data. Some data arrives that has to be processed by the system. Second type of stimuli is events. Some event happens that triggers system processing. Events may have associated data, although this is not always the case. That means behavioral models show what will happen when our system receives a data or an event as a trigger. Then what the reaction of the system is the behavioral model. Many business systems are data processing systems that are primarily driven by data. That means the stimuli in many business systems are data. They are controlled by data input to the system with relatively little external event processing. In this case, their processing involves a sequence of actions on that data and the generation of an output. We may consider an example, a phone billing system. To have a phone billing telephone billing. That means how much we will pay for the phone, for example. This system will accept information about calls made by a customer, calculate the cost of these calls and generate a bill to be sent to that customer. You see, the system need to know how many calls we have made during a month or a year or etc. And we have to know the cost of each call, and then we can calculate the cost of all the calls, the costs of all the calls during a certain period, and then we can generate a bill to be sent to the customer. This is a data-driven system. By contrast, for real-time systems are often event-driven with minimal data processing. For example, a landline phone switching system responds to events such as receiver or hook by generating a dial tone, or the pricing of keys on a handset by capturing the phone number, etc. That means, in the same domain, when we want to have the behavior of responding to our phone, to our call, we need to have an event like the phone songs. Then we can respond to it by pressing the key. These are event driven. For data-driven models, we show the sequence of actions involved in processing input data and generating an associated output. Here, these models are particularly useful during the analysis of requirements, as they can be used to show end-to-end processing in our system. That means, with data-driven models, we can see the entire sequence of actions that take place from an input being processed to the corresponding output, which is the system's response. It means that with data-driven modeling, we can see the flow of data. And with this one, we know the process of the system. Here we have an example. This figure shows the chain of processing involved in the insulin pump software. In this diagram, we can see the processing steps represented as activities and the data flowing between these steps represented as objects, like this. You see here, a purchase officer fill in an order. Here, order is an object. Then this order should be validated. If it is okay, then we'll update the amount according to the budget. We save the amount in the data store orders. Then we send the orders to supplier. You see here, with this activity model of the insulin pumps operation, we know the chain of processing involved in this system. And we see the processing steps like these activities, and the data flowing like the order, budget, etc. We can consider them as objects too in our programming in our object-oriented programming language. Here we have another way to show the sequence of processing. That means we can use this kind of, we can also consider this figure as a UML sequence diagram. Here we see how these activities can be used to model interactions. But yeah, we have to draw these so that messages are only sent from left to right. Then we show the sequential data processing in the system. You see here, in this figure, we use a sequence model of the processing of our order and sending it to a supplier. Yeah, we can read it in detail. For blood sugar sensor, we can from the object blood sugar sensor, we can get sensor value. Here we get sensor data to compute sugar level. Then we get blood sugar level and we can calculate insulin delivery. After calculating, we receive insulin requirement to calculate pump commands. Then we have these control commands. We control the pump and we get insulin pump. You see here, we describe the flow of data and the activities also. This kind of modeling, we call it data-driven modeling because, we see along the process the flow of the data. Now we'll see another perspective, which is event-driven modeling. As we have said before, real-time systems are often event-driven with minimal data processing. For example, a landline phone switching system responds to events such as receiver or hook by generating a dial tone. Yeah, this example we have talked about it earlier. And event-driven modeling shows how a system responds to external and internal events. Event-driven modeling is based on the assumption that a system has a finite number of states and that events or stimuli may cause a transition from one state to another. Yeah, you see here we consider the events as stimuli, not anymore data. These models the behavior of the system in response to external and internal events. The UML supports event-based modeling using state diagrams. Yeah. And these models show the system's responses to stimuli, so are often used for modeling real-time systems. State machine models show system states as nodes and events as arcs between these nodes. When an event occurs, the system moves from one state to another. So we see with the state machine models, we show system states, like here, system states and events that cause transitions from one state to another. And we do not show the flow of data within the system, but we may include additional information on the computations carried out in each state. State charts are an integral part of the UML and are used to represent state machine models. Yeah, we have state charts. to represent state machine models in UML. Here, this figure is a UML state diagrams of a microwave oven. This is an example of control software for very simple microwave oven to illustrate event-driven modeling. As we know, real microwave ovens are actually much more complex than this system, but the simplified system is easier to understand. You see here, this simple microwave has a switch to select full power or half power, a numeric keyboard to input the cooking time, a start, we have a start or stop button, and a screen to display the information. We can consider the sequence of actions in using the microwave is, at first, we select the power level, either half power or full power. Then we input the cooking time using a numeric keyboard. At last, we press start and the food is cooked for the given time. And we have here, as we see, we have some conditions. As for safety reasons, the oven should not operate when the door is open. And on completion of cooking, a buzzer, when we finish cooking, a buzzer will be sounded. The oven has a very simple screen to display various alerts and warning messages. So in this state diagram, we see that rounded rectangles like these, they represent system states. They may also include a brief description. Following this do, we can describe the actions taken in each state. For example, for full power, we say we set power at 600. For half power, we set power at 300. The labeled areas like this represent stimuli that force a transition from one state to another. We can indicate start and end states using field circles. Like here, the field circle to represent the start statement, and field circle rounded by a circle to indicate end states. It's just like in activity diagrams. So we see, we'll read this state diagram in detail. Here, the system starts in a waiting state and responds initially to either the full power or on the half power button. Users can change their mind after selecting one of these two kinds of power and press the other button. That's why we have two transitions here. Then we set the time. If the door is closed, the start button is enabled. Pushing this button starts the oven operation, and the cooking takes place for the specified time. This is the end of the cooking cycle, and the system returns to the waiting state. Else we have if the door is not closed, it's open, then we can close it. Oh yeah, this will enable the start button of the oven and will start the operation. The same thing. As we see here, we can use the UML notation to indicate the activity that takes place in each state. Sometimes we need a detailed system specification to provide more detail about both the stimuli and the system states. Here, we will introduce a tabular description of each state and how the stimuli that force state transitions are generated. We see here, as we have seen in the diagram, state diagram, we have different states like waiting, half power, full power, set time, disabled, abled, enabled, operation. We describe each state. The oven is waiting for input. The display shows the current time for the waiting state. Half power, we set 300 watts and the display shows half power. Correspondingly, for the full power, we set 600 watts and we show full power. We can also set time. We have the cooking time is set to the user's input value. The display shows the cooking time selected and is updated as the time is set. We have the state disabled. Oven operation is disabled for safety. Interior oven light is on. Display shows not ready. We have the state enable where oven operation is enabled. Interior oven light is off. Display shows ready to cook. And we have the state operation. That means oven is in operation. Interior oven light is on. Display shows the timer countdown. That means the time of cooking is decreasing. On completion of cooking, the buzzer is sounded for 5 seconds. Oven light is on. Display shows cooking complete where buzzer is sounding. So you see here we have brief descriptions of each state. We have also the descriptions for each stimulus. Yeah, here, as we say, we have different events as stimulus in this system. Like half power, the user has pressed the half power button. When we press the full power button, we have the stimulus at full power. Timer, when the user has pressed one of the timer button, that means we set the time. Number, the user has pressed a numeric key. Then we have different stimulus like door open, door closed. When the oven door is open or is closed. Start, when we press the start button, we have the event start. When we press the cancel button, we have the event, the stimulus or trigger, cancel. So you see with this tabular description, we can have detailed system specification, including more detail about both the stimuli and the system states. We have a problem with state-based modeling. That is, the number of possible states increases rapidly, especially for large system models. So sometimes we need to hide detail in the models. How to hide details in the models? One way is to use the notion of a superstate that encapsulates a number of separate states. This super state looks like a single state on a high-level model, but is then expanded to show more detail on a separate diagrams. For example, here, in this diagram, we can consider the operation. Here, in this diagram, we can consider for this operation state, we can consider it as a super state, and we can expand it. We'll see how to expand this state operation. You see this figure. Here, we illustrate the operation state. This operation state can include a number of substates like checking, cook, alarm, dumb, disabled, waiting, etc. Here we show that operation starts with a status check, and that if any problem are discovered, an alarm is indicated and operation is disabled. Cooking involves running the microwave generator for the specified time. On completion, a buzzer is sounded. If the door is open during the operation, the system moves to the disabled state as shown here. You see, for just one state, we can expand it in detail like this. So that's what we say. For a large system, we can use this. Yeah, we can use the notion of super state, like operation here, to encapsulate a number of separate states. In this way, we can simplify the entire sequence, the entire state diagrams. Okay, this is for this part. For the behavioral model, we have talked about the data-driven modeling and event-driven modeling. Okay, if you don't have some questions for the moment, have a break of 10 minutes. Hi, welcome back. Okay, so we'll continue. Here, in the last class, we have talked about the behavioral models. And we say the behavioral models are models of the dynamic behavior of the system as it's existing, as it is executing. And behavioral models is to represent the system from a behavioral perspective. We have talked about the two types of stimuli to which the system should respond. These two types of stimuli are data and events. That's why we have data-driven modeling and event-driven modeling. For data-driven modeling, we have an example of insulin pump operation to show the activity. With the activity model of this system, we see the flow of the data. And for event-driven modeling, we had an example of microwave oven, and a small, which is the model-driven engineering. Model-driven engineering, it is an approach to software development where models rather than programs are the principal outputs of the development process. And these programs that execute on a hardware or software platform are then generated automatically from the models. Proponents of model-driven engineering argue that this raises the level of abstraction in software engineering so that engineers no longer have to be concerned with programming language details or the specifics of execution platforms. You see here, For model-driven engineering, we focus on the models, and we do not pay too much course on the code, on the development of on the programs. That's the idea of model-driven engineering. That's why we say here, engineers no longer have to be concerned with the programming language details or specifics of execution platforms. We can have a higher level of abstractions because we use only models to represent the system. Model-driven engineering is still at an early stage of development, and it is unclear whether or not it will have a significant effect on software engineering practice. So for the moment, we don't use this idea too much in the daily life, in our professional career. It is a perspective, a foresee, and we have several arguments for and against model-driven engineering. For model-driven engineering, model-based engineering allows engineers to think about systems at high levels of abstraction, as we have said before. So we don't need to concern for the details of their implementation. This will reduce the likelihood of errors. This will speed up the design and implementation process. And we are allowed to for the creation of reusable or platform-independent application models. Secondly, with model-driven engineering, by using powerful tools, system implementations can be generated for different platforms from the same model. Therefore, to adapt the system to some new platforms to some new platform technologies, it is only necessary to write a translator for that platform. In this way, all platform independent models can be rapidly rehosted on the new platform. So generating code automatically means that it is cheaper to adapt systems to new platforms. These are arguments for, that means to support the model-driven engineering. We have also some arguments against model-driven engineering. As we have said earlier, models are a good way of facilitating discussions about our software design. However, models they don't always follow that the abstractions that are supported by the model are the right abstractions for implementation. As said here, models for abstraction are not necessarily right for implementation. So we may create informal design models, but then go on to implement the system using an off-the-shelf configurable package. And secondly, savings from generating code may be outweighed by the cost of developing translators for new platforms. That means the arguments for platform independence are only valid for large, long lifetime systems where the platforms become obsolete during a system's lifetime. However, for this class of systems, we know that implementation is not the major problem. Requirements engineering, security, and dependability, integration with legacy systems, and testing are more significant. So we may have other costs rather than generating code for model-driven engineering. Now we'll see the model-driven architecture, which is important in model-driven engineering. Model-driven architecture was the precursor of more general model-driven engineering. It is a model-focused approach to software design and implementation that uses a subset of UML models to describe a system. Here, models at different levels of abstraction are created. From a high-level, platform-independent model, it is possible, in principle, to generate a working program without manual intervention. That means, with model-driven architecture, we can have different levels of abstraction. And if the level of abstraction is high, then we may have a platform-independent model, which may be possible to generate a working program automatically without manual intervention. We don't need human to intervene in the activity of generation. It will be generated automatically. The model-driven architecture method recommends 3 types of abstract system model. The first one is a computation-independent model. These models model the important domain abstractions used in the system. These type of models are sometimes called domain models. We can develop several different computation-independent models reflecting different views of the system. For example, there may be a security computation-independent model in which we identify important security abstractions, such as an asset and a role and a patient record computation-independent model. And there we can describe abstractions such as patients, consultations, etc. Second type of model is a platform-independent model. This model, here we model the operation of the system without reference to its implementation, as what we have said before, independently. The platform-independent model is usually described using UML models that show the static system structure and how it responds to external and internal events. And the third type is the platform-specific model. Here, these models are transformations of the platform-independent model, that in this one, with a separate platform-specific models for each application platform. In principle, there may be layers of platform-specific models, with each layer adding some platform-specific details. The first level of platform-specific models could be middleware-specific, but database independent. So when a specific database has been chosen, a database-specific, platform-specific models can then be generated. In this figure, we illustrate a final level of automatic transformation. We see here a transformation is applied to the platform-specific models to generate executable code that runs on the designated software platform. We see here for each we have a computation independent model with the translator and domain specific guidelines. We can have the platform independent model with the help of translator. platform-specific patterns and rules. We can have the platform-specific model, and with the translator language-specific patterns, we can automatically transform this one to executable code. In fact, the translation of platform-independent models to platform-specific models is more mature, and several commercial tools are available to provide translators from these platform-independent models to platform-specific models. We can also find some commercial tools to provide translators from this one, the platform-independent models, to some common platforms like Java or J2EE. Like here. In this figure, what is showed here? We have the platform-independent model. And with some commercial tools, we can provide the translators to some platforms like J2EE or Java. These rely on an extensive library of platform-specific rules and patterns to convert the platform-independent models to the platform-specific models. There may be several platform-specific models for each platform-independent model in the system. If a software system is intended to run on different platforms like J2EE or NET, then it is only necessary to maintain the platform-independent model. The platform-specific models for each platform are automatically generated, as shown here in this figure. Now we'll see the Agile methods and model-driven architecture. In fact, the relationship between Agile methods and model-driven architecture is not easy. The developers of model-driven architecture claim that it is intended to support an iterative approach to development and so can be used within Agile methods. The notion of extensive upfront modeling contradicts the fundamental ideas in the Agile manifesto, and new Agile developers feel comfortable with model-driven engineering. If transformations can be completely automated and a complete program generated from a platform-independent model, then in principle, model-driven architecture could be used in an Agile development process as no separate coding would be required. You see here, in fact, so far, there are no model-driven architecture tools that can support practices such as regression testing and test-driven development. That's also why we say model-driven engineering is still at an early stage. Okay, this is for the model-driven architecture. Now we'll see the executable UML, and we see the fundamental notion behind model-driven engineering is that completely automated transformation of models to code should be possible. To achieve this, we have to construct graphical models whose semantics are well defined. We need a way of adding information to graphical models about the way in which the operations defined in the model are implemented. This is possible using a subset of UML2 called executable UML or XUML. Here, we'll simply present a short overview of the main features of this subset. Yeah, as we have said before, UML was designed as a language for supporting and documenting software design. It is not a programming language. Yeah, as we have seen, the designers of UML, they are not concerned with the semantic details of the language, but with its expressiveness. Yeah, with the UML diagrams, it's more easy to have the communication. That means we can express it on the ideas more easily with people from different backgrounds. And here we introduce useful notions such as use case diagrams to help with the design, but which are too informal to support execution. So to create an executable subset of UML, the number of model types has therefore been dramatically reduced to these three key model types. The first one is the domain models to identify the principal concerns in our system. These models are defined using UML class diagrams and include objects, attributes, and associations. Here, when we see these elements, objects, attributes, and associations, can you think of something we have learned in this chapter? For the domain models, as we have said here, we can use UML class diagrams and we can include objects, attributes, and associations. It's like our structural models. We have also used the class diagrams and we have some associations between the classes. The second key model type is the class models. Here we define classes along with their attributes and operations. And the third type is state models, where a state diagram is associated with each class and is used to describe the life cycle of this class. Yeah, here clearly it's like our behavioral models. Yeah, there we have state models with state diagrams. We see that the dynamic behavior of the system may be specified declaratively using the object constraint language, or may be expressed using UML's action language. In fact, the action language is like a very high-level programming language where we can refer to objects and their attributes and specify actions to be carried out. It's this part. It's the features of executable UML. Now we'll have a brief summary of this chapter. In this chapter, we have said that a model is an abstract view of a system that ignores system details. Complementary system models can be developed to show the system's context, interactions, structure, and behavior. So you see here, we have clearly mentioned or revised the four perspectives to represent a system.